So hello again. Tonight we're going to talk about a little bit of stellar dynamics or astrodynamics, or where things are in space and how they move. I'm just referring to this as a look ahead. So here's what we're conceptualizing or visualizing. You're on Earth somewhere on a specific date and time, and you're looking at something in the sky. In the future, where would the Earth be in order to look at the same place in the sky? And then where would you be looking sort of to turn back around and look where you were, or where you were, where do you look in the sky to find where the Earth will be? Yeah, I know as far as, you're not going to see yourself, so it's ludicrous. But there's a lot of motions going on. So when somebody says something like, a day is 24 hours, kinda. A year is 365 days, kinda. So we'll get into the actual numbers of all that stuff and how it's affected. And as a side note, if you remember the pulsar timing array that allowed us to detect the gravitational wave background, the way we could finally accomplish that was by knowing the amount of gravitational effect Jupiter and Saturn have on the position of the sun as the focus of our solar system. When Jupiter is swinging its way around the solar system, the center of gravity of the sun is not in the center of the sun. It's actually right out to the surface of the sun, thanks to the gravity of Jupiter pulling on the sun. So lots of things moving around. So as I was saying, in space, everything's in motion. Some motions are small, like daily rotation. Other motions are very large, like the solar system orbiting the Milky Way galaxy. Some motions are only small when you look at them over a very short period of time. You look up in the sky and you see the moon, and then you come back half an hour later and go, yep, the moon's moved, but not very much. So if you look over longer periods of time, like pick a particular motion and then look at it hours, days, years, or even centuries over time, you can see really how much it moves. So small things add up, and big things exhibit big differences. And the motion of things. So when something pulls on something, how far does it move? Can something as big as the sun move? And as it turns out, not a lot, but yes, it's measurable. So we know the Earth rotates on its axis daily. We're no longer of the Earth-centered universe. We know that the Earth orbits the sun annually, as do the other planets in the solar system. We know that the Earth is tilted on its axis, and this kind of gives us our seasons. We know that the equator of the sun, for whatever reason, is slightly tilted from the plane of the solar system. It's only a small number of degrees, but the equator of rotation of the axis of the sun actually has a small tilt to it. So the plane of the solar system is not precisely the plane of the rotation of the sun. A little bit of difference. And when you're doing stuff measured over long periods of time or very high speeds, all these little values add up, and they're very significant. The plane of our solar system is tilted relative to the plane of the galaxy. So if you've ever looked at galaxies in the night sky, you know that there are galaxies that are facing towards us, and they look very pretty. And then there's galaxies that are almost 90 degrees to us, like the sombrero, and all you see is edge on and a bulge in the middle. Yeah, not everything's lined up along the same lines. We did a presentation earlier this year on, and out in the universe, nothing is up or down. It's just whatever it is. And it's only your perspective under gravity that allows you to go, well, my feet are down and my head is up. And as soon as you go out into space in your space capsule, like the International Space Station, two astronauts in the ISS can be opposite each other. And now which one's right side up? Doesn't matter. Orientation is a matter of perspective. So we know that our solar system is in a spur branch of one of the major branches of our galaxy. But that spur moves in and out over long periods of time. The branch moves in and out, and the spur along with it. and then the entire galaxy rotates around like a giant whirlpool. If you're just looking at something localized, like tonight, what's up in the sky, you don't have to think about a lot of those things. But if you're looking at where will it be a year from now, you start off to take into account those things. How is it you don't feel all these motions if they're going so fast? It's because gravity holds you to the Earth. The atmosphere sort of comes along for the ride with you, unless there's a breeze. The individual motions relative to one another are fairly slow from your perspective. You don't feel the fact that the Earth is rotating on its axis over 1,000 miles per hour. So instead of looking back on yourself, wouldn't it be easier to just go someplace else, like go to the moon, and then you can look where Earth was, and then you can look where Earth will be in the future? Yeah, you can do that, but now you've added a third body, and the moon has its own set of motions. So when you're looking back and you want to know where to look back, the Earth is always got the moon facing in the same direction. What if you're on the far side of the moon? You'd never see the Earth. Oh, okay. So it's all relative to your perspective, and adding another body doesn't simplify things. It kind of complicates it. So I put together a laundry list of collective motions, and there's individual slides that will specifically enumerate them. And we have a reference model here on the table behind me that we can actually look at. So we know the Earth rotates on its axis daily, goes around the sun annually. We know that the Earth is tilted on its axis. We know that the sun orbits the Milky Way galaxy. We also know that in the spur of the galactic arm, there are gravitational forces that take the solar system and make it bob up and down within the arm of the galaxy over long periods of time. You'd think you get nauseous from all this, but you don't. We don't notice it because, the sun drags the Earth along with it, just like we don't notice the Earth rotation because the gravity drags the atmosphere along with us. So if you add all these things together, it does affect the Earth's climate. The Earth seasonally moves closer and farther from the sun. And the orbital shape, everybody thinks the Earth orbits the sun on a circular orbit. It's actually a slightly elliptical orbit. And the shape of that ellipse, as we're on the sun side of the ellipse, changes a small amount because of the gravity of the sun. And then we're on the far side of the ellipse by that small amount. It widens out a little bit because the sun's gravity, it's an ellipse, so there's two focal points. The sun's at one of them, and there's nothing at the other one. So when you're coming around the curve, so to speak, at the other one, there's less gravity there, so that ellipse kind of opens up a bit. But there are cycles that you can look at over 41,000 to 100,000 years, and you can actually see that these collective motions do have an effect on the Earth. They cause things like ice ages, global floods, and they shift things from being lush landscape to desert droughts and all that kind of stuff. You can see the cycles on it. We've watched that cycle, and it's not cycling. It just keeps going up. So the thing they always like to say, it's all just natural. Those are Milankovitch cycles. Well, Milankovitch cycles do have a cycle period, and it's going the other way at the moment, and we're going the other direction. So this is an interesting phenomenon. There's a thing called a solar day, which is our commonly referenced definition. It's a 24-hour day. But since the Earth is going around the sun at the same time that it's rotating on its axis, if you wanted to look at the same spot in the sky, you don't look at it 24 hours later. You look at it 23 hours, 56 minutes, and 4 seconds later, a little less than a day. So you don't think about it. But, nature is not as precise as our technology. So we'll occasionally have to throw in an extra second on December 31st. And here is the U.S. National Institutes of Science and Technology, NIST, formerly the U.S. National Bureau of Standards, years ago. This is their clock rolling over with an extra second added. the clock should never get to 60. It went 23, 59, 59, and then it should go to 0. No, it went 23, 59, 59, 23, 59, 60. They added an extra second. They don't do this all the time. They just do it when the technology is much more precise than nature is. Here's your first, think about it, perspective. Let's say we've picked our day. We're going to look up in the sky. We're going to see something at night. Well, when I'm looking up at the sky at night, and then in the future, as the Earth goes around the sun, I look up in the sky, and maybe a slightly different angle, but I look at the same thing in the sky. Could I just turn around and look at where the Earth was? No. Well, in the past, could I look to where the Earth would be in the future and see that same spot on Earth? No, because the Earth rotates and it's tilted. So if I'm at my starting day and I'm looking up in the night sky, my part of the Earth is facing away from the sun because it's night. So the Earth in the future, if I wanted to see the same part of the sky, I would be looking 180 degrees away from where the Earth was, because in the future, that part of the Earth is looking at the night sky as well. So there's no way I can look back at myself. There's no way to look in the future and see where I would be, except if you see the green arrows at the bottom. Instead of looking straight overhead, if I looked down along the horizon, so from my starting point, I would look towards the western horizon. And in the future, if I wanted to look back, I'd look towards the eastern horizon. And then I'd have a potential of having these two things line up. We've got the physical model I'll show you towards the end. You know, we'll do all the PowerPoint stuff, and then we'll show you the physical model. And it's pretty obvious. The physical model kind of like, it's a dead giveaway. So this is what I was just saying is, if you think you're just going to look out in the sky and see where the Earth would be, no. So here's another aspect of, it's not just the solar day versus the sidereal day. It's also, it's not exactly 24 hours, folks. And it's, you know, they'll talk about the year being 365 days and a quarter. Well, it's not even a quarter. It's actually 0.24. It's actually 6 hours and 9 minutes. So we take this into account by saying, well, every 4 years we throw in a February 29th. You know, it's a leap year. We put in February 29th, which is leap day. But that's too much, actually, which is why the actual calculation for leap year says it's not just every 4 years, it's every 4 years if the year is divisible by 100, but not 400. So if the year is divisible by 100, but not 400, okay, we'll throw in a leap day. But if it's divisible by 400, that's too much. We'll not throw in a leap that year. So it's not always you're going to have a February 29th every 4 years. But if it's only divisible by 400, depending upon when you were born, you may never see one of those. So here's what I was talking about, the Earth orbit around the sun. So on the left, you see a slight ellipse, and the sun is at one focal point, and there's nothing at the other focal point. And you can see that the distances aren't that much, as, you know, 91,400,000 versus 94,500,000. That's millions of miles. So it doesn't look like much in the overall scheme of things, but it's millions of miles. So as the Earth is moving towards either of its solstice points, that's where the ellipse stretches out its longest, and it's stretched out longer at aphelion, which is in July, than it is around January, which is perihelion, because the sun's at that focal point. So the curvature of the ellipse is not a uniform curvature around the circumference of the ellipse. It's pinched on the sun side and fatter on the opposite side of the sun. So you probably have heard of precession. This is the old Earth spinning like a top, and the north pole of rotation moves around every, so many thousands of years, 26,000 years, you'll do a full circle. But the tilt actually varies from 22.1 to 24.5 degrees. But we just call it 23.4 average. We don't want to be precise unless we actually have to do something like that. But how many people knew there's actually a smaller, more recurring wobble than precession?
Oh,
It's called nutation, and it's from the moon.
huh.
So the moon is in orbit around the Earth, and that orbit is not a perfect circle. It's also a slight ellipse. And because the Earth is tilted on its axis, and the plane of the orbit of the moon around the Earth is also tilted against the ecliptic of the solar system, that means that when it's swinging around and it's on like the heavier side, it can pull a little bit. And when it pulls a little bit on the Earth, that changes where the North Pole is pointing by a small fraction of a degree. The overall range of nutation is 18.4 arc seconds. And each wave of the nutation is 18.4 years. It's just a mathematical coincidence that they're the same numbers. But one is in arc seconds and one is in years. But you can see this, you can see the sort of like top effect of the Earth, that's precession. And then within the top effect, you've got these little wiggles. Those wiggles are courtesy of the moon. And some of the better planetarium software applications will actually take into account not just precession, but nutation. How many knew about this one? Apsidal precession. The Earth is not only going around the sun, the orbit of the Earth is rotating around the sun. So you can think of it like petals on a flower.
Mm.
So the orbit of the Earth around the sun draws out an ellipse, and the ellipse is moving in a direction over a long period of time. The even better planetarium software will take into account apsidal precession. All these little tiny movements that are actually not small. They're thousands of miles per hour in different vectors and such. But if you wanted to plot, let's say, where the Earth is going to be in the future, it's not just where in its orbit, where's the orbit going to be? So now we can make a slightly better guess. So we know about the rotation and the tilting and the sun and all the other things that affect it, and the ellipse and all that stuff. So, but you wouldn't be able to look at yourself anyway, because let's say you pick nighttime for both of them. We already know that if you're nighttime on both of them, one's looking out in the sky and the other one's also looking out in the sky. So there's no way for you to look at each other. But if you knew exactly where to look in the sky and you wanted to wave at yourself, so to speak, and took all these things into account, how quickly would you have to do it? Well, let's see. The Earth now is rotating at over 1,000 miles an hour. The Earth then is also rotating over 1,000 miles an hour. So the angular velocity of the two rotating Earths are such that you have to know exactly when to wave, and the guy on the other Earth would have to know exactly when to wave back at you. The amount of time you'd have is a small fraction of a second before things are out of alignment. Being a little bit off can affect things, even on shorter periods of time. Here's something you have to think about. The Earth is a gravitational mass. There's stuff that moves that is part of the Earth, like air. The air volume changes because mountains get in the way, and you can have a high pressure or a low pressure zone on one side of a mountain or the other, and that means there's more air molecules over there than there are over here as the weather changes on a daily basis. Rain. Hey, we had huge thunderstorms in Florida, and it was dry out in the Southwest. The rain has mass. That's gravity. These masses do affect a day on the Earth. What about the earthquakes you don't feel? if an earthquake moves a tectonic plate by a half a millimeter, probably would not even notice it. But a half a millimeter of something that is gigatons of rock, that's a giant shift in mass. So that affects the daily rotation of the Earth. But by how much? They've actually done a study. They use what is known as a square frame laser interferometer. It's a giant square frame, and it's maybe 20 feet on a side, and they run lasers and bounce the mirror, kind of like the gravity wave detector. They split the beam, they send it out and back, and then they join the two back up, and it creates an interferometer. So if the torsion on one side or the other of this perfectly square frame is such that you can measure the difference down to, like, as the saying goes, smaller than a gnat's hair. This would be like 1/1000th of a gnat's hair. How much time would it change the duration of a day? They actually measured this. Plus or minus 55 thousandths of a second over a 120-day period. Small. Or if you divided it out, it comes out to be about plus or minus 19 millionths of a second per hour. 19 microseconds per hour. And you think, that's a small amount. Nobody worries about that. My Raspberry Pi computers can calculate using GPS signals time of day down to 10 billionths of a second. So millions of a second is a big fat number. So if the Earth speeds up or slows down by 19 microseconds per hour, how much is that over the surface of the Earth? Let's say you're standing at a place on the Earth, and where would you need to be standing given this 19 microsecond per hour difference? It's about a third of an inch. If you were doing time travel or matter transfer or something like that, you want your hallway or wherever you're arriving or departing from to be a little larger. You want some, like, as the saying goes, you want some shoulder room, because if you didn't take this into account, you could be arriving a third of an inch into a wall. Not good. I mean, you can be fully in the wall. So I was thinking, if you wanted to do this sort of spatial displacement travel or time travel, then, we were talking about all these other factors, tilts and rotations and precession and nutation, and now you have to take into effect the gravitational mass of the Earth and how material sloshing on the Earth can add plus or minus a third of an inch on a daily basis. If you did want to transfer from one place to another, you want to pick a building that's long-standing, like a historical reference, and you want to go into a part of the building that doesn't change over time. Turns out, bathrooms. If you go into really old buildings, they change all kind of rooms and furniture and wall hangings and, knock holes in walls, but because of the plumbing as an anchor, they can remodel the bathroom, but the center of the floor, not in the stall, but the center of the floor of the bathroom has no walls around it for feet, and it doesn't change. That's a good place. And I thought back for a while, and there was actually a short-lived sci-fi show on TV where they took this into account. I wasn't thinking of it at the time, but the only place they could do time travel arrivals was in bathrooms of historic buildings. I'm like, that's kind of weird. Not kind of weird. There's actually science behind it. But if you didn't want to arrive in bathrooms, you could pick like a large cement-covered area, like an open park space. But you want to make sure that there's no obstructions when you go there, because if it's an open park space, people could be walking around. Somebody could.
Well, did somebody screw up with the Philadelphia experiment?
Well, in the Philadelphia experiment, which was science fiction, they didn't get the ship back in exactly the same position as all the people that were on board it. The people materialized while the ship was still in a state of flux. So people arrived, and the gravity of the Earth pulled them down into what was essentially the hull of the boat. And then everything solidified. So yeah, not good for those people. But it's things you have to think about. If I'm in a car and I'm transferring my car across space, I want myself and the car to arrive at the same time. I don't want to be out of phase. Because if I arrive early and the car is not quite solidified yet, gravity's going to pull on me. And then if the car solidified, I'd be buried inside the bottom well of the car.
Yeah. Yeah.
Aspirin at
True.
the ready yet? But here's the one that really takes the whole mental exercise and throws it into a can. If you take into account all of the movements that I'm aware of, and you said, I want to be able to get back to where I was, like, okay, every year we can look up at the night sky at roughly the same time of the year, same day, month, and see that particular constellation. Not exactly. Close, but not exactly. And if you ever look at the coordinate system for stellar objects, you'll see a J2000 on the end of the coordinates. So right ascension, declination, J2000. Based upon all the known movements, including the movements of that star, that's where the star was as of the year 2000.
Uh-huh.
2000's 20 plus years ago. Things have moved since then.
Yes,
If
they
you look
have.
at your astronomy software and you look at the right ascension and declination, if your astronomy software can take into account all these movements, you'll be able to select the difference between J2000 and J now. And what J now is, they take the J2000, add in all the known movements, and conclude what its new coordinate's going to be. Now, for most things, the difference between J2000 and J now, not much of anything. Barnard's star has a very large transverse velocity, meaning it's moving across the sky. About every 10 years, they have to adjust its coordinates because not only is everything else moving, it's moving almost 90 degrees to us across the sky. So it's going to have a higher angular velocity from our viewpoint than normal stars and galaxies and stuff. Everything's a moving. You got to take it all into account if you want to be accurate. Of course, if you're just going, look, there's the moon in the sky, you kind of don't have to be all that accurate. But if you're going, I want to send people to the moon and get them back safely, you need to start taking these things into account.
Yeah.
Now, showing you pictures in PowerPoint, it's kind of what I do. But I said, some people may not get this. So I cooked something up. I made a physical thing. So I took a couple of globes. I took some machine parts. I took some wooden skewers, some camera pipe clamp brackets, and some aluminum tubing, and a giant piece of plywood that I painted black. And here's two globes, the aluminum rod you see down at the bottom, that represents the orbit of the Earth around the sun. The one in the back is the Earth in the past. That's this one. The one in the, I bumped the camera and the camera focus went out. There we go. The one in the foreground, that's the Earth kind of in the future. You can see the black bracket holds the globe at the tilt of the Earth. And as the Earth goes around the sun, that tilt doesn't get affected because of gyroscopic action. So the Earth in the back and the Earth in the front are both tilted the same amount. And they're both looking at a particular point in the sky. But that point is kind of in the midday afternoon. Even though they're both pointed at the same place in the sky, it's not at night, because if it was at night, the two globes would be in shadow. There, like that. Now, you couldn't see the place on the Earth because that's at night. So I have these long wooden skewers sticking out to let you know where they're looking. Now, this happens to be the place in the Earth's orbit closer to an equinox, a spring or an autumnal or fall equinox, because that's where the shape of the ellipse of the orbit of the Earth around the sun is flattest. It's more of a straight line. But if you said, well, I want the dates to be farther apart, you can see the pipe on the ground starts to bend around as the Earth in the past is more towards the equinox place, and the Earth in the future is more towards the solstice, winter or summer solstice. This is more like the winter. This is the summer solstice. So the sun is at the focal point here. You can't quite see it from this angle, but both of the Earths, the tilt is aligned with the same place in the sky. There's a straight line running between the two. So now if I said, I want to look at the nighttime of both of the globes, they're now both at night, and they're both, you can see from the sticks, they're both pointing out in the same place in my white board, which is the night sky. I should have made that like a galaxy or something, put a big star on it. Things
That would be
should be out for a few, but you can see that as the position of the Earth goes around the curve, that if you want to look at the same part of the sky, you have to take into account a number of different factors. And now if I wanted to look at the same place on the Earth from the past into the future, and I said, well, I'm going to look back at the Earth from the future. I'm going to look out at the Earth from the past. Check that out. Even though the latitude position is the same for both of them, the fact that the globe is tilted means when I'm in night on one side, I'm not going to be looking at the same place in three-dimensional space as the daytime I am looking on the other side. So not only is it like, what can I see at night versus what can I see in the daytime? It's what's the tilt angle that I'm at so that I know what I'm looking at. That's why the sticks aren't looking at each other, because the Earth is tilted. Any other what ifs? Like, what about if I pointed them both at the daytime? What if I pointed them both at the sun? Look, the solar eclipse is happening. Everybody in the past and in the future are looking at the solar eclipse. When they're both pointing at something out in space, you can get the sticks to line up. But when they're pointing at each other, they won't line up. Or as I used to have out at the observatory, somebody would bring up an equatorial mount telescope and say, I can't get it to point at anything. See how that big black curve lines up the angle of the equator? Well, until you get your telescope mount lined up with the angle of the equator or the North Pole, you can't point it except at a few things, those things that are open to the direction you're pointing. Now there are more. Okay, so in conclusion, everything in space is moving. An expectation of returning to the same spot, like same time next year, presumes a very local reference, because since the galaxy's moving across the universe, the actual three-dimensional spatial place in the universe is never going to be a place you're ever going to be back at again. Even if you think about where we are in our orbit around the sun, since the solar system rotates with the galaxy, even though you came back the next year, yeah, you're roughly in the same place in the sky as the Earth orbits the sun, but you're not at all in the same place as the solar system goes around the galaxy. There are small things that make small changes, and there are big things that make big changes, depending upon what you want to do with your positioning definition. You either need to definitely take that into account, or you can fudge it and get by with that. With it. Okay, how many hours in a day? 24. Okay, you're obviously not an astronomer. The spatial position vagueness, as in, notice I didn't give you an exact date and time when you can look in the future and see where the Earth is going to be, because I don't want to go through all that math. It would make everyone's head hurt, because there are equations. It's just a thought exercise. But if I could do it, why would it be something I'd ever want to consider doing? Because the Earth moves around the sun at a speed much slower than the speed of light. But the speed of light, very much faster, travels through the solar system. And if a TV broadcast in radio frequency says, and here's tonight's lottery winners, if you could actually receive a signal from the future, they would never broadcast another lottery. So if you knew exactly where to point your radio telescope to be able to pick up a signal from a broadcast TV station that was pointed in your direction at precisely 10 p.m. on the night of the drawing, then you could receive a signal from the future, much like when we talk about, if I look out into the universe, I see the past. Yeah, you can see the past in radio too. since it's so impractical to actually do that, it's not worth the effort to try. But what is important is we've learned that there's a lot of minutia in astrodynamics. There's a lot of minutia in pointing at things and getting telescopes to actually point at and track things in the sky. Where you really have to pay attention to it is if you're doing spatial displacement kind of things. And, that's why I say when you travel in time, you also travel in space, and you need to take into account both of them. Okay. So did you like the visual aid?
Yeah. Nice.
Yeah, I thought I was just going to knock that out in like 3 or 4 days. It took more than 2 weeks to mentally try it, realize the parts I needed to buy, what I needed to modify.
Trips to Home Depot.
Yeah.
Yeah.
Okay, I better play the next 2 pages, otherwise I won't have the things to edit. And of course, lots of links. So many links, I just spread it across 2 pages.
Mm-hmm.
Yeah. I even have a link to the square frame laser interferometer that measures how far off Earth's rotation is. I want to give you the pleasure of going through all of the wading into the rabbit holes and minutia that I do. So if it's something I looked up and I went, that's interesting, I got to provide a link to that. I'm sure there's somebody out there that will want to follow that link. Now, when you go to the YouTube site and you look at one of the videos for Broward Astronomy, in the description section are the actual hyperlinks.
Mm-hmm.
So you can click on them there.
Yeah, I just want to make sure today you found it so interesting what's going on with us. We should be really dizzy with all that movement.
Well, gravity and the fact that everything's coming along for the ride really means we don't feel it.
Right. But there's a lot of stuff going on around us. My goodness me.
And now I'll stop sharing. Anything else anybody wants to talk about before we get done? Yeah.
Want to stop recording?
I will stop recording because you may want to say something.